Today's presentation is about learning algorithms while solving problems. We'll start with a simple problem and give multiple solutions to the problem with different complexities. And in the process, we'll illustrate the usefulness of designing algorithms and analyzing their complexities. The first problem that we are targeting is maximum subsequence problem. Let's define the problem. Given a sequence of integers a1 through an, the objective is to find the maximum possible value of a subsequence ai through aj. The list of integers will contain at least one positive number. However, it can have 0 or more negative numbers. And the solution should be the sum, which is maximum for all possible contiguous chunks. In this case, here is an example. You have a list of integers, and if you work it out, you will see that 11, minus 4, and 13, those three, and that sequence from a2 through a4 gives the largest sum, that is 20. We want to write a program that will find that out. In the process, we'll explore 4 different algorithms with 4 different complexities, and we'll keep on improving the runtime complexities as we move along. And this will illustrate that why it is so important to analyze the algorithms before you implement them. Because the first one is order of n cubed. So for a very large n, that means the list of integers is very large. For example, n equal to 10 to the power 6, the algorithm may take more than 10 years to complete, so it's thoroughly impractical. On the other hand, the fourth or the smartest algorithm will finish in a fraction of a second. Let's start with the most naive and brute force implementation. In order to find out the maximum subsequence, one of the easiest way to do is to find out all possible subsequences and then pick the max. That's precisely what this algorithm is doing. It's going over the list once, and for each of those it's going over the list again and then again. So it's figuring out between I and j what is the sum and whether that sum is greater than maximum sum, and then storing the sum. Because it has 3 for loops, each with the maximum length of n, and they are all nested, it has a complexity of order of n cubed. Now see whether we can improve on this. Do we really need this innermost loop? We don't need the innermost loop, because if we know the sum from ai to aj minus 1, we can compute the sum of ai to aj by simply adding the jth element. So we don't need a third loop to compute I to j, the sum. So by eliminating the innermost loop, we can reduce the complexity to order of n square. And that's precisely this algorithm is doing. It's going over the loop twice, figuring out the maximum sum. But this is still order of n square, and for a very large n, this is not practical. Can we improve this further? The answer is yes. By splitting the list into 2, we can split the list using divide and conquer paradigm. Split the list along the midpoint, search the maximum subsequence in the left half, then for the right half do the same. But does that suffice? The answer is no, because you may still end up with a case where the maximum subsequence spans both the halves. So not only you have to find out the maximum subsequence of the left half and the maximum subsequence of the right half, but also you need to find out the maximum subsequence that spans both the halves. First 2 are easy because you are making recursive call. Third one, finding out the straddling sequence, is the tricky one. However, there is a key observation. A straddling sequence must include the midpoints. So in this example, the straddling sequence must include -2, which is the last integer of the left half, and -1, which is the first integer for the right half. So the straddling sequence is the maximum subsequence which ends with -2 at the left half, and maximum subsequence which starts with -1 for the right half. And if we just simply combine those two subsequences, that gives you the straddling sequence. So the algorithm is fairly simple. You just split the list in two, call it recursively, and then compute in linear time the straddling sequence. And if you solve this equation, it will give you order of n log n, which is a huge improvement compared to order of n cubed that we started with. Now, can we improve it further? I'll give you a time to pause and think over it. What are the properties of the maximum subsequence? And remember that in the beginning I mentioned that for this specific problem instance, there is at least one positive number in the list. Now, a maximum subsequence, can it end at a negative point? No, because the last point you are adding to the subsequence is not adding to the value. So it cannot end at a negative point. Now, can a maximum subsequence have a prefix which is negative? A prefix of a subsequence is another subsequence, and the sum of a prefix is the sum of the elements of the prefix. Can it be negative? The answer is no, because if we simply take out the prefix, which is negative sum, the remainder of the subsequence will have a higher value than the original subsequence. And that defeats the definition, because the definition of a maximum subsequence is the maximum sum. So a prefix of a maximum subsequence can never be negative for this specific problem instance. And that simplifies the problems a lot. All you have to do is to scan the list and then keep adding the numbers. The moment the sum is less than 0, you can simply reset it, because that's not going to be part of any subsequence. So simply keep adding the numbers. If it's more than maximum sum, you keep storing it, so that's keeping track of the maximum sum. The moment this sum becomes less than 0, a prefix which is less than 0 can never be part of a subsequence. You can throw it away, and that dramatically reduces this